Hear that? That was 40 hertz, the audio frequency. And that sound, along with a much more pleasant one, could one day alleviate epilepsy by altering the music in our brains. So what? Oh, there's my face. So what do I mean by music in our brains? Well, our brains make music, sort of. At the very least, they have rhythm. Neurons that operate together in a network electrically fire together. And this coordinated firing in multiple networks results in repeating patterns or oscillations of electrical activity known as brain waves. So there are 5 kinds of brain waves, and they're named for their frequency. So we have delta, theta, alpha, beta, and gamma. And these waves are oscillating in our brains at various times and in various places. And we measure brain waves using electroencephalography. Whew. Or EEG, through electrodes placed on a person's scalp or sometimes even inside of their brains. So brain waves are associated with specific neural processes, and we think that synchronization of different brain waves helps different parts of our brain communicate with each other. So, for example, gamma and theta waves, which both occur in the hippocampus and in the frontal neocortex, have been observed to sync up, and we think that might have roles in cognition and memory. We've also noticed, and brace yourselves, that our brain waves sync up to external stimuli that occur at similar frequencies. So, for example, flickering lights, music or sounds, even rhythmic finger tapping. And this means that we can consciously expose ourselves to rhythmic stimuli to alter our brain activity. Okay,
Ooh.
So this is, first of all, totally ridiculous, but it also has real potential to treat or at least reduce symptoms in patients with neurological diseases. And there have been lots of studies over the past few decades exploring this potential. So I'll give you one example from a lab at MIT, looking at treating Alzheimer's with light that flickers in a gamma frequency. So gamma waves are significantly reduced in the brains of Alzheimer's patients. And applying this light therapy in mouse models of Alzheimer's cleared protein aggregates, or plaques, that are a hallmark of Alzheimer's, restored memory and learning ability, and literally prevented neuron death. And that's what's shown here. So these are images of mouse brains with different cell types and different colors. And the main thing to note is this black, oh, there she is this black gaping hole where brain should be. And it's only in the Alzheimer's mouse, but it's not present in the control, normal mouse, and it's also not present in the Alzheimer's mouse that received light therapy for an hour a day. So just blinking lights rescued neurons from dying. It's crazy. And I mentioned epilepsy as a disease folks are studying this phenomenon in, and there are numerous studies showing that brainwave syncing stimuli, particularly of an auditory nature, could reduce the number and frequency of seizures in epilepsy patients. So one such study came out last year from the Epilepsy and Cognition, or ECOG, lab at Dartmouth. They previously saw positive effects from playing that 40 hertz sound that you just heard for epilepsy patients, but the only problem was, like you, the patients did not enjoy it. They were like, can we listen to anything else, please? So in hopes of finding a more pleasant sonic experience with the same therapeutic effects, the researchers turned to Mozart!
Somebody in the audience said Taylor Swift.
Maybe not yet.
Very much the Mozart of our age.
Mozart's a lefty. It was on the slide.
Hi.
Hey.
Woo! Yes, there we go. Perfect. Man, it's true. You can't catch a break. But to poll the crowd, has anybody here heard of the Mozart Effect? Anybody? Hands up. Yes. And all of the early millennials just outed themselves. So yes, the Mozart Effect was a really fun romp in pop pseudoscience that happened in the mid-90s. So the idea came from this one study where they played a Mozart piece, the Sonata for Two Pianos in D major, K448, for some undergrads before they did a spatial reasoning test. The very, and I want to emphasize, very modest results of that study appeared in headlines as Mozart makes you, and also your babies for some reason, smarter, prompting the creation of Mozart self-help books. Oops, sorry, wrong one. There we go. Self-help books and mixtapes and headphones sized to fit pregnant bellies, I presume, and prompting the governors of Georgia and Tennessee to spend upwards of $100,000 on Mozart CDs for school kids in their states. Turns out they can follow the science and fund public education when it suits them. Maybe it's a branding thing. I don't know.
Hey.
This fad, along with inconsistencies in the protocols and tech used in research about K448, the Mozart piece, and epilepsy, left the Mozart Effect shrouded in skepticism for a number of years, until, equipped with fancier tech, bright young minds, and an eclectic playlist, the ECOG lab revisited it. So here's what they did. They enrolled 16 human participants, all with drug-resistant epilepsy, and played each of them clips from the following playlist. Mozart, K448. Other classical stuff, Wagner, Liszt, yada yada. Violet Noise.
I'm not familiar with yada yada. Is that
Yada yada.
very
You have to
famous
listen
composer?
to him. It's truly changed the game. Violet Noise, which is like a high-pitched frequency that increases with time. K448, but with some frequencies filtered out, and then 3 songs from the participants' preferred genre, with or without some lower frequencies artificially boosted. So the purpose of all these options, along with the filtering and the boosting, was to pinpoint exactly what musical features produced the Mozart effect, and to see whether the effect was actually unique to Mozart K448. So, as participants listened to the music, the researchers measured how frequently they experienced IEDs, which are these unique spikes that appear. Oh my gosh! No, I spoiled the joke. Sorry.
Everybody act like you didn't see that.
You saw nothing. Shh.
I missed it, so
You need to
it'll be the first time
laugh
for me.
so hard.
Perfect. I'm relying on you, Devin, for all the laughs. But they're just these brief spikes that appear in EEGs of epilepsy patients. And the idea was that a potentially therapeutic song would reduce the number of IEDs, excuse me. So to briefly examine the preferred genre thing a little further, so the options were country, heavy metal, and rock and roll, which, like, okay, fine. But one of the 2 heavy metal songs was Nickelback, which seems squarely at odds with their goal of finding enjoyable music. You know they omitted that from the grant proposal. But they don't even show data collected during the Nickelback song. Here it is. Though I have to imagine it looks something like this.
Hey! Amazing.
Thank you. You're all very kind. Here's what they learned. At least 30 seconds of listening to the original, unfiltered Mozart K448 reduced IEDs by 2/3 in participants. Wow, cool. Literally everything else did bupkis. Mozart won. All other popular music since the 18th century, but especially Nickelback, 0. So what gives? What's so special about K448? Well, the researchers analyzed the musical features of K448, like harmonies and timbre, and they divided the piece into segments based on these features. So the boundaries between segments are the points where the music shifts or changes direction. And that's shown in this image here, which is admittedly like way too high level for me to totally understand. But it shows how the segments appear across the sound frequency spectrum. So you see these kind of clear sort of edges, like in that kind of pink gradient, that demarcates the boundaries between the segments. So to kind of look at this a little more myself, I picked a boundary that they identified, and I figured out where it happens in the sheet music. And sure enough, there's definitely a musical shift. So the green box over the boundary matches the green box in the sheet music, and you can clearly see that just by looking at the notes, one melody ends, and then you have the boundary, and then another completely different melody begins. And the researchers noticed that whenever participants heard one of these boundaries, their frontal lobes started cranking out lots of theta brain waves. And from prior studies, we know the same kind of brain activity happens when we feel a positive emotional response to music and when we are confronted with sudden changes in music, in things like volume, tempo, or key changes. And in both situations, we also pay more attention to the music. So the hypothesis is that when we listen to Mozart K448, it sounds nice to us. It makes us happy. So we listen to it more closely, and then it catches us by surprise and defies our expectations, so we listen to it even more closely. And all of that translates to this heightened activity in our brains that might be therapeutic for patients with epilepsy. So there are still, of course, lots of questions to be answered, and we're a ways away from being prescribed playlists or light shows. But in light, not even intentional, laugh at my own jokes, of all the ways that music already helps us to connect, to cope, to express ourselves, it's kind of amazing to think that someday it might even help us tune up our brains. Our amazing pianists, Rose McCatherine and Ryan Breckmacher, will now grace us with an excerpt from Sonata for Two Pianos in D major, K448. And I encourage you to please feel free to groove along with your brain waves as you listen, but also equally free to clap and cheer and holler like they did in Mozart's day, by the way. This stiff, like proper listening to music silently. No. Get rowdy. That's how it's supposed to be. And it's warranted. As mentioned, this sonata rips. So.
Hell yeah. Woo! Woo!
Woo-hoo. This part's so good.